Okay, we're back to a situation like the one where we saw the ball being dropped and the tile descending on the ball, and that actually causes the ball to speed up. Just discovered I have a Mountain Dew leak on my desk. It causes the ball to speed up, and also to bounce back and forth between the two walls, considering the two pieces of tile as two walls, with a fairly high frequency. Now, the ball really is about a 10-gram ball, so we're going to analyze what would happen if that super ball bounced back and forth between two walls, moving at 4 meters per second. Now, what you saw there, I don't think the ball was moving at 4 meters per second. If it was moving at 4 meters per second, it would be able to bounce about a meter high. Now, I didn't take the tile away from it, but I think if the tile was taken away from the ball as the tile descended, the ball would bounce maybe half a meter high, higher than from the distance from which I dropped it, because the tile is lowering on the ball and hitting it each time, which speeds it up each time. So the ball is going to speed up progressively until the tile stops, and then of course it's going to start losing energy because it's not a perfectly elastic. The collision is not perfectly elastic. Okay, well, anyhow, we're going to assume the ball is, we have ideal perfectly elastic collisions here. The ball is moving at 4 meters per second, about the speed it would move if it was able to bounce up a meter, or the speed at which it would move if it was dropped from a height of a meter, roughly hip high. So a 10-gram ball at 4 meters per second, and striking each wall 15 times every second. Now, I don't think we had a frequency of 15 times a second, although we were probably in the range of 10 times per second in some of those demos. But you understand the situation. And of course, we've got the walls horizontal here just because it's a little easier to label. Okay, now, don't read what I've done. Work this out. Stop, work it out. I will tell you that you're going to use the impulse momentum theorem. So you want to start by figuring out the momentum of the ball and then figuring out how much the momentum changes. You should work that out independently. Simple application of the impulse momentum theorem. You should review that if you don't know it. Okay, well, whether you've done that or not, here we go. Okay. The momentum of the ball has a magnitude of 4 meters per second times 0.01 kilograms, which is 0.0104 kilogram meters per second. It's not a Newton, it's a kilogram meter per second. A kilogram meter per second squared would be a Newton, so if you like, this is a Newton per second. A Newton times a second. And we'll use that fact a little bit later on, but you don't need to worry about it right now. Okay, 0.04 kilogram meter per second. That's the momentum of the ball, the magnitude of the momentum. Now, we have to take the direction of the ball into consideration. Is the momentum this way, or is the momentum back this way? Well, okay, that's the magnitude of the momentum. The change in momentum at a collision is what? Okay, well, I say it's 0.08 kilogram meter per second because that was a response I got from a couple of students. The change in momentum is what? Well, now we're talking about the change in momentum, not the change in the magnitude of the momentum. The magnitude of the momentum doesn't change on collision. Again, we're assuming an ideal perfectly elastic collision. So before the collision and after the collision, your speed is 4 meters per second and the magnitude of your momentum is 0.04 kilogram meters per second. However, the momentum itself is either positive or negative. If we take this direction to be the positive direction, then a momentum in this direction is positive, a momentum in this direction is negative. And if we go from a positive momentum to a negative momentum, we have a negative change in momentum. From a positive momentum to 0, If we went from 0.04 kilogram meters per second to 0, the change would be negative 0.04 kilogram meters per second. And then we'd turn around and we'd have another negative 0.04 kilogram meters per second to go from 0 to negative 0.04. Okay? Now, the change in momentum is then negative 0.04 kilogram meter per second minus 0.04 kilogram meter per second. That's the final momentum, negative 0.04, minus the initial momentum, which is positive 0.04. So we get a negative minus a positive, gives us a negative, and the negative 0.08 kilogram meter per second. So it's going to either be this, if the momentum is initially positive, or it could be this. It could be if the initial momentum is negative, that would mean you're talking about a collision with this wall, you would have an initial momentum of negative 0.04 kilogram meters per second to be subtracted from the final momentum of positive 0.04 kilogram meters per second. And you want to make sure you understand that. Otherwise, this whole model doesn't make a lot of sense. Okay, in this case, of course, this calculation is going to give us a positive 0.08 kilogram meter per second. And that's very relevant because, well, let's go ahead and get the force. It's very easy to get the average force now. You divide the magnitude of the force, the average force, is the magnitude of your change in momentum, not the change in the magnitude of your momentum, because the magnitude of your momentum doesn't change, but the magnitude of the change in momentum, which is going to in either case is going to be 0.08 kilogram meters per second, divided by your delta t. Your delta t between collisions is 1/15 of a second. So we're going to be dividing 0.08 Newton seconds, and I'm using the Newton seconds here instead of kilogram meter per second, but you can verify that that unit is the same as this unit. If I divide that, well, I get 15 times 0.08 newtons, or 1.2 newtons of force. Now, if we're talking about the force being exerted on this wall, we're talking about the change in momentum being negative 0.08 kilogram meters per second, meaning that the force is going to be negative 1.2 newtons. We would divide this negative change in momentum by the 1/15 of a second to get a negative 1.2 newtons. And it's obvious that this wall is going to have to exert a force in this direction to change the velocity of this ball, so that that force is in this direction. Similarly, in this case, the collision would be with this wall, and the force would have to be positive.